Hi guys, myself Akash. Today I'll be explaining about pigeonhole principle and pumping lemma for regular languages. Let's consider a situation where there are 9 pigeonholes and 10 pigeons. So 9 of the pigeons occupy all the 9 pigeonholes and the 10th pigeon is searching for any left out pigeonholes. But since no pigeonhole is left out, the only possibility is to enter into already filled pigeonhole. So this natural intuition is what pigeonhole principle explains. So let's go through the pigeonhole principle statement. The pigeonhole principle statement goes this way. The pigeonhole principle states that if we must put n plus 1 or more pigeons into n pigeonholes, then some pigeonholes must contain 2 or more pigeons. So though this pigeonhole principle looks very trivial, but it has got lot of applications. One of the important application of pigeonhole principle is the pumping lemma. So pumping lemma is basically used to prove that a given language is not a regular language. A language is said to be a regular language if we can draw any finite automata to that language. If we are not able to draw any finite automata to that language, then the language is called as a is not a regular language. Let us understand this concept in a more deeper way. So let us take an infinite regular language L. If a language is finite, then we can always draw a DFA for it. Hence, such languages are always the regular languages. But we can't say an infinite language as regular or non-regular until we are able to draw a finite automata to it. So let us consider that infinite language L is a regular language. So since we are assuming that infinite regular language L, so hence we must be able to draw a DFA for it. So let's say that our DFA has M states as represented in the figure. Now let us take a string W with W belongs to L. So since W belongs to L, if we traverse the W, we must be able to reach the final state of DFA since W satisfies or belongs to the L. If if we take a condition that the length of the string is greater than or equal to number of states of a DFA, then with the help of a pigeonhole principle, by relating the length of a string to the number of pigeons and number of states to the pigeonholes, we know that there would be at least one pigeonhole with more than one pigeons. In similar way, there would be at least one state which would be repeated. Let that Q be the first state which is repeated. Now here we can split our string W into XYZ. X representing the states which are before repeating state and Y representing the set of repeating states and Z representing the states after the repeating states. So this y being the representation of a set of repeating states, this repeating state itself creates a characteristic for the infinite languages. If this repeating state was absent, then the remaining state would just form the finite string, which is always regular. So from the figure, we can observe that length of xy string is always less than or equal to m, and since there is at least one repeating state, so length of y is greater than or equal to 1. So if we carefully observe, then our DFA which we have drawn would be satisfying xyz string and xyz string and x triple y z string and x 4y z string. So in a general way, if we try to conclude, then our DFA will satisfy all the strings which are of the form y power I z, where I value goes from 0 to infinity. So all the three conditions, that is length of xy less than or equal to m and length of y greater than or equal to 1 and all the strings which are of the form x y power I z would be part of the language regular language L. So if any of these conditions are violated, at least one of these condition is violated, then we can say that the language is not a regular language. But still, if all the three conditions are satisfied, we can't say that the language is the regular language. So because pumping lemma is basically used to prove that a language is not a regular language, but not to prove that a language is a regular language. So let us go through the statement of pumping lemma. If A is the regular language, then there is a number P, which is generally called as a pumping constant. So where if S is any string in A of length at least P, where P we can assume that in our discussions that P represents here the number of states of a DFA. Then S may be divided into three pieces, that is x is equal to x, y, z, satisfying the three conditions we have already discussed. That is, all the strings which are of the form x, y power I, z, where I greater than or equal to 0 must belong to A, and length of y must be greater than or equal to 1, which is greater than 0, and length of xy must be less than or equal to P, that is number of states of a DFA. So hence pumping lemma is basically used to prove that a given language is not a regular language. So let us understand the concept of pumping lemma using examples. Let us consider the first example. Prove that L is equal to AB power 2i, where I value goes from 1 to infinity is not regular. So we will be proving this language L is not regular by using pumping lemma. So let us consider the pumping constant to be 4. Since the pumping constant is 4, we can consider the string of length greater than or equal to 4 according to the pumping lemma. So we have considered the string of AB, 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 whose length is 8. So now we can split the considered string into x, y, z according to the pumping lemma conditions. Now the split can be this way: x is equal to AB and y is equal to A. Both x and y splits would be satisfying the condition of pumping lemma, that is length of xy less than or equal to p and length of y greater than 0, which is here 1. And the remaining string z would be BA, BAB. So if we consider uh, the string x, y square z, so it is clear it is AB double is then followed by BA, BAB. So it is clearly not in the form of AB power 2i, where A must be followed by B and it must be it must be concatenated with following ABs, but we have two A's concatenated, so which indicates that the given string is not in the form of AB power 2i. Hence we can say that L is not a regular language because one of the condition of pumping lemma is violated. Let us consider the example 2. Prove that L is equal to W, which belongs to A comma B whole star, such that number of A's in W are less than number of B's in W is not regular. So we will be proving that L is not regular using pumping lemma. So let us consider the pumping constant to be 5. And since the pumping constant is 5, we can consider the string of length greater than or equal to 5. So we have considered A power 5, B power 5. Now we can split the considered string into x, y, z such that they satisfy the pumping lemma conditions. So I can split x is equal to a, y is equal to a. So which would basically satisfy mod xy to be less than or equal to p, which was 5, and mod y greater than 0, which is 1. And the remaining string would be equal to z. Now, if we consider the string x, y square z, so it will generate the string that is a power 6, b power 6. So which is clearly violating the condition uh, of the regular language which we have assumed, that is number of a's in w less than number of b's in w. So but in our case we are getting number of a's in w to be equal to number of b's in w. Hence we can, since one of the condition of pumping lemma is violated, we can say that L is not a regular language. Let us check if language L is equal to a power n, b power k, c power n plus k such that n greater than or equal to 0, k greater than or equal to 0 is not a regular language using regular pumping lemma. So in jflab software, so first we'll be entering the pumping constant. So let that pumping constant be 4. So once have entered the pumping constant, the software itself has determined the string whose length is greater than or equal to 4. So I'll be decomposing the W as follows. So I've chosen X to be A, Y to be A. So and Z is the remaining part of the string. So if I click on set XYZ, here we can see that. So it has pumped the string. It has found the string which violates the language L. So we can see the animation here. So we have considered the string X, Y square Z. So if we try to see the step-by-step pumping of string, so X I have considered once. Since Y I have considered twice, so I'll be pumping it twice. And Z I have considered once. And it has produced the following string where the number of A's are 5, number of B's are 4, and number of C's are 8. So it is clearly violating A par n, B par k, C par n plus k, since 5 plus 4, which is 9, is not equal to uh, immediately followed number of C's, that is 8. Hence we can say that the particular string x, y square z is not in language L, and since it violates one of the conditions of pumping lemma, we can say that language L is not a regular language. Let us check if language L is equal to AB whole power n, A power k, such that n greater than k and k greater than or equal to 0 is not a regular language using regular pumping lemma in jflab software. So I'll be entering the pumping constant as 3. So here we can see that the software has generated a string whose length is greater than or equal to 3. So I'll be decomposing x and y, the string w into xyz. So I'll be choosing x as ab and y as a, and the remaining part of the string would be z. So if I click on set xyz, so here we can see that the software has found a string which is not part, which is of the form x y power I z, where is greater than or equal to 0, and still it's not present in the language L. So let us understand it by animation. So it has considered x y power 0 z. So if we try to see the step-by-step computation, so x is taken once, y is taken 0 times, and z is taken once. So it has produced the string, the following string. Since this following string is not present in the language L, and since it violates one of the condition of pumping lemma, we can say that the language L is not a regular language.